Good morning, I am Krishna Kumar from Krishna's classroom. Today we take up the discussion of the so-called invertible operators. Now last time we proved the following result, namely that if, of course, we generally agree to work on finite dimensional vector spaces. So V is assumed to be a vector space over a field F of dimension. This is one assumption. Generally, we work with finite dimensional vector spaces. Let W be a vector space of these are the general conditions. Now we have the following result. Let VW. Now we assume that means both V and W are vector spaces of dimension n. If T is invertible, then the inverse of T, denoted by T inverse, is a linear transformation from W to V. That is, T inverse belongs to L W. Now this is what we proved last, and in fact you have the following scenario. That means you have V, W, both of the same dimension. T is invertible. That means T is 1 to 1 and positive. Then T inverse exists as a function from W to V, and this function we have shown that is linear. So T inverse is defined from here to here, and this is V, this is TV. T inverse is defined from, and T inverse is linear. So that's what we proved last time. And you see that T inverse is defined from W to V. And then you also observe that T inverse T t is equal to I, the identity operator. So also T of T inverse, both these are defined and this is equal to I of T inverse of T is first you have T and then T inverse. The other one goes around in the opposite direction. First T inverse and then T. So you start from W and reach W itself. So this is equal to I to T. So this is what we proved last time. Now we define a related concept called singular operators. Now before that we observe a certain thing, namely, suppose U, V, W are n-dimensional vector spaces over, let T belong to L, U, V, S belong to L, V, W, and both T and V, T and S are invertible. Then you know that T inverse is defined from W. So this is the scenario that we have. It is invertible, so you have T inverse defined from here, S inverse defined from here. Then you see that the composition of T and S is defined. So what you have, S composition T is given. So ST is defined from, ST is essentially S composition T is defined from U to W, and ST is 1 to 1 and on to. This follows from the bijection property of T and bijection property of S. So that needs a proof, of course, but I leave it you to prove this. Similarly, therefore, ST inverse exists as a function, and this turns out to be what is called T inverse S inverse. This also requires, and it's not difficult to do this, right? And this needs a few lines. Now, note that this does not require T and S to be if that is the existence of, I mean the existence of inverse. Because even if S and T are not assumed to be linear, but just one-to-one and on-to, their inverses are defined, and this relation holds without the assumption that it's linear. However, what happens is that if S and T are linear, then ST is linear. So also ST inverse is linear. So also you see T inverse is linear, S inverse is linear, therefore T inverse, S inverse is also linear. So the linearity is something that comes as or inherits from the corresponding linearity properties of the operators. And you know that T inverse S inverse is defined from, see T, what is called ST is defined from U to W. T inverse S inverse is defined from W to U. Okay. So T inverse S inverse is both a left inverse of ST as well as right inverse of ST. Observe that T inverse S inverse, which is equal to, is both right inverse as well as left inverse of ST. Because T inverse equal to I U and so also Now we also make certain observations. We are working with the finite dimensional vector spaces. Now before that, we introduce the concept of singular operators or non-singular operators. If T is linear and one-to-one, then we have T of u minus v equal to 0 if and only if u equal to or equivalently T of u equal to 0 if and only if u equal to 0. Now we shall define that T is non-singular. T is non-singular if u equal to 0 implies u equal to. This is the definition. And this means that null space of T consists of only the 0 vector. So we see that we have T is 1-to-1 if and only if T is not singular. Now let us do the following. Let LBW, that T is non-singular if and only if each linearly independent subset of T is carried to a linearly independent us assume that T is non-singular and then prove this. Okay, so we prove this. Then we have zero. Now we try to prove this. Each linearly independent subset of V is carried to a linearly independent subset of W. So let independent now consider T V1 so the question is this linearly independent? So let us compute this. So let now this you know T is linear, therefore this is equal to T of okay, and T of C1 P1 plus etc. Ck Vk equal to 0 implies C1 V1 plus C2 V2 plus etc. Ck Vk is equal to 0. So T is assumed to be non-singular. Equal to 0. And this implies C1 equal to 0 equal to 0. What does that mean? Hence Tv1 is a linearly independent set. Now let us consider the converse. So hence T singular implies each linearly independent subset of V is carried to a linearly independent subset of W. So now we prove the converse. This is the proof of the forward integration. Now we prove that assume T carries linearly independent subsets of subsets of W. Now choose any. Now we prove that P is non-zero. Okay, so let V be equal to C1 V1 plus okay, it's quite easy to prove. Let then the singleton V is a linearly independent subset of now by the assumption that T carries linearly independent subsets of V into linearly independent subset of W, TV is a TV is a linearly independent of W, which implies TV is not equal to 0. Thus, TV is not equal to 0. This property of this equivalence may be sometimes useful. Okay, let us now look at some examples. Very fascinating example you have. See, let invertible. Now define T from Ax. T inverse belongs to and this defined by and you know that invertible n by n matrix maps linearly independent sets in P to linearly independent sets. And that's the constitution. Take the example 2. This is an infinite dimensional vector space. There are a lot of nice things happen for various operators. So let F be a of complex field, some subfield can be the whole of C. So we write V to be a set of all polynomials over the field F. That means all polynomials with coefficients from F. Consider the differentiation operator it's a formal differentiation operator D defined by D of P equal to where for some reason. Now you can easily see that this is an infinite dimensional vector space. I think F is a subfield of C. Yeah. So here we are taking V equal to PF and D as this one. Let P from defined by again you can see that it's a map from PF into PF. That is very easy to check. And T is linear, therefore T belongs to LPF. Now observe that B maps all constants to 0. Therefore, D singular. D is singular. Now we can define the right inverse of T. Let us define it the following way. How do we define it? Let E be from defined by E of you write this as this is just integration. Okay, this is writing the indefinite integral. Then E is the indefinite is the integral operating on one can show that E is linear. It means, see, what you are doing here is this integral this is what we are doing. Then E is linear. So E belongs to that is E belongs to. Now we compute that DE however, so that means DE equal to identity operator. However, ED in fact constant polynomials zero. That is ED is zero. Now consider P P of now P is non-single. Why? Because P now one can define the left inverse of T. How do we define that? Let S belonging to be defined by S of to define this as P1 plus to verify that it is linear. I mean, essentially this condition is it's quite easy. You drop the first constant and then divide by or take x out and then you throw it out. So that's what it is. Then you can easily check that yes, P is defined and turns out to be equal. But now you see that S of a constant function E naught, this is equal to 0. It's clear. Okay. So similarly, and because of that, Ts of a constant function is also 0. Therefore, Ts is single. Equal to 0. Ts of P naught is again equal to 0. Therefore, we have okay. Now note that is infinite dimension, and therefore don't expect things to go straight away. This non-singularity to define what is called invertibility, etc. in infinite dimensional spaces. Because the right inverse may exist, the left inverse may not be defined at all, and these kind of things happen. Now we look at what happens if the space are finite dimensional. So we have the following result. On finite dimensional vector spaces. We assume, so we shall prove the following theorem. Let finite dimensional over the field, and we assume dimension of both are of the same dimension. If T belongs to, take any linear transformation E to the W, then the following statements are equivalent. That means what we are exploring in this result is the various equivalent forms of the condition for invertibility. So we have the following conditions. One, T is invertible. Two, T is onto, that is range of T, that is null space of T. Is a basis for D. Then TD1 is a basis for D. Where X is some basis Now these are 5 different statements. Now T is invertible, means T is 1 to 1 and onto, and naturally everything follows. That is T inverse X is an inverse function and then it is linear. Now T is non-singular. Now we want to show that T is invertible, then T is non-singular. So prove if you assume 1, T is then T is on. Therefore T inverse exists and T inverse is linear. All those things we have proved. Since T is linear, T inverse is linear. Therefore T is invertible. Now we want to show that T is non-singular. Now you see that, we have this following results, namely from the prime nullity theorem, dimension of V. Therefore, what do you get? See, already you are assuming T is onto. T is onto means what? The range of T is dimension of W equal to 10. Dimension of V. Therefore, null space of T zero. That is so, which implies this. Now you can use the same argument that if T is non-singular, then range of T is equal to W. Reverse that. Then you see that assuming 2, one can, from the rank nullity theorem, we have, what do you have? Range of T and this is equal to dimension of W. Therefore, now assume let we are assuming so finite dimension. We are assuming this one. Now T is onto. Therefore, it follows that T V1 spans W. Why? Because any V is of the form C1 V1 plus C2 V2 plus etc. Cn Vn, and then if you apply T, you see that it's a linear combination of TV1, TV2, etc., TVN. And since T is onto, that's what we are assuming. So every element, any element in W can be expressed as a linear combination of TV1, TV2, TV. Okay. So start with an arbitrary element of W. It is the image of some V from V. V can be expressed as a linear combination of V1, V2, etc., Vn. Now, you see W is TV, which is a linear combination of TV1, TV2, etc., Tvn. That's the proof. Okay. Therefore, span of W and dimension of W is equal to N implies TV1 and is now assume 4. What is the assumption? V1 is a basis, then TV1 is a. Of course, it follows from the fact that there exists a. This implies 5. So this is now assume 5. Let now suppose V belongs to V is such that TV equal to 0. Now we have to show that V is then equal to to 0. So V is equal to now TV equal to C1 TV1 Tn. Hence since V1, TV1, TV2, etc., TVN form a basis, the linear independence of which implies equal to 0. Therefore, one to one. Therefore, once again, using the Riemann nullity theorem, we have since dimension of V equals to dimension of W, therefore dimension of which implies therefore RT is a subspace of W such that dimension of RT equal to which implies that is T is solved. So T is both 1-to-1 and ordered. So we have cyclically we have proved this. One is 2, 3, 4. That is the equivalence of this 5 statements. Hence, the 5 statements are equivalent. So that completes the proof of that. Now let us consider, so we have let V be a vector space dimension over 50. Let invertible form P. Then we have P inverse equal to P inverse P. This we have. Okay. Now let us consider. So let us consider the set of all invertible operators over E. Right. So let's write down. So V is, as we have assumed, it's finite dimensional vector space. Then X has X with respect to multiplication is non-commutative. Now this is in general statement. There are certain situations it becomes commutative. So in general it's a non-commutative because we have, you know, P belonging to X, S belonging to X, then Tx, Ts and St are defined. And as elements in X. A lot of things are to be proved. T is invertible, S is invertible. So you take Ts and St, they are also both 1 to 1 and 1 to 2, therefore the inverse exists. And we have in fact Ts inverse equal to S inverse T inverse. Well defined. And I belongs to X. And we have Ti plus Ti equal to It equal to T. And we have T into T inverse I. So the inverse operator exists because T belongs to and this property is easily verified. And also you can show that this is in general non-commutative. It is associative. In the sense that T1, T2, I can write T2. This is simple to do. Therefore, it's a multiplication group. So this is it does not mean that all the entire NB consists of invertible operators. So in general, X is not equal to, there exists operators which are not invertible. Even non-zero operators are there which are not invertible. There exists for example, so let dimensions this. Okay. Now any V can be written as X plus Y now define or assume both proper subspaces of define then T belongs to what I mean to say is that apart from the zero operator, there exists non-zero operators which are non-invertible. Okay, so I think we conclude here our discussion on invertible operators. Okay, thank you very much.